Hello everyone, I'm Anissa Kheireddine and I will present you a new way of solving SAT-based bounded model checking problems. This is a joint work with Etienne Renault and Souheib Baarir. Before going into details, let's start by explaining what is the model checking. To illustrate this term, here we have an SMV program that translates the behavior of a microwave and the finite state representation of this system. The program is composed of two Boolean variables. The variable start is set to true when the microwave is launching. The variable close is set to true when the door of the microwave is closed. The variables are set initially with the value false, and all the possible actions of the microwave are set in the switch cases. So for instance, the two colored arrows express two possible situations. For the first one, for the blue arrow, it expresses the fact of closing the door only, and the red arrow expresses the fact of launching the microwave even though that the door is not closed, and so on for the other transitions. So as we know, in a microwave, it is not possible to turn it on while keeping the door open. This case should not happen, and in the SMV program, we can express this undesirable situation in a simple linear temporal logic form. From these two information about the transition relation of a system and a property to be verified, model checking procedures will evaluate the possibility of reaching an undesired state violating this property. So model checking procedure will guarantee the reliability of the behavior of a given system by performing checks on sets of properties. However, enrolling all the state transition relation will quickly consume a lot of memory, especially when dealing with very complex problems. So to avoid this state space explosion, we will recall a variant of model checking called bounded model checking. Instead of enrolling all the transitions, we can limit ourselves to a number of states reachable in atmos k transition. For the same property we want to verify, which is always launching the microwave with the door closed, at k equal to 0, the only reachable state is the initial state. At k equal to 1, we can reach up to 2 states, including the state that violate the property. So this bound k that we fix will check if the property is verified on the first k transition only. If no state violates the property, the bound is increased and the process is repeated until reaching the termination case. This approach has the advantage of being representable in a Boolean SAT formula where the variables represent the literal of the original problem and the clauses encode the constraint associated to the transition, meaning the model, and the property. Each clause is a disjunction of variables, and the final Boolean SAT formula will be expressed in a conjunctive normal form, meaning a conjunction of clauses. So this CNF formula is then given to a SAT solver that finds out if a witness of length atmos k exists that verify the property. For our research, we focus on conflict-driven closed learning solvers such as Maplecomb's solver. Beforehand, let's explain how CDCL algorithm works. It gets the Boolean formula as input and returns SAT, meaning that an assignment of the variable exists satisfying the formula. Otherwise, it returns unsat, saying that no assignment is possible. For the sake of this study, we are interested in two main components of the algorithm, the Boolean constraint propagation and the conflict analysis phases. So the CDCL algorithm will perform a backtrack search, selecting at each step a decision literal, which is set to a Boolean value, and this assignment is followed by an inference step that deduces and propagates some unit literals assignment. This is what we call the Boolean constraint propagation procedure, BCP. This branching process is repeated until finding a solution or reaching a conflict. In this latter case, a learned clause is generated by a procedure called conflict analysis, and this learned clauses is stored to be reused in the future. However, the number of generated clauses can be exponential, so a question matters to us on how can we refine the election of learned clauses to store only relevant ones. We observed that SAT procedures do not take advantage of the characteristic of the original problem, especially to identify interesting learned clauses. As far as we know, most modern SAT solver uses heuristics to identify these irrelevant clauses, such as linear blocking distance (LBD) and or the size of the clause. Other studies focus on other parts of the algorithm, such as variable ordering, branching heuristics, or use of symmetries. The focus of our research is the definition of what a relevant clause represents. We propose a methodology to use structural information of the BMC problem to determine relevant clauses. We build from that new heuristics dedicated to the BMC, and we integrated the approaches on a SAT solver which show promising results. So let's put back the previous SMV program. We can divide the variables of the program into three groups: the variables related to the model, the one related to the property that translate the property, and finally new fresh variables used for conversion. This latter consists in translating the proposition into Boolean formula. So for example, the expression of setting the variable clause to true. We will call these variables junction variables. And this results in a classification of the clauses of the SAT formula into 7 classes. The CM class will represent the clauses that contain variable from the model only. CMG classes correspond to the clauses that contain a portion of variable from the model and the other from the junction, and so on. So far we have been able to extract a new feature of a clause. So let's study the impact of each class by measuring the usage rate of the learned clauses during both propagation, BCP, and conflict analysis phases of the CDCL algorithm. In addition to this new measure, we also log the LBD value of the learned clauses. This value consists in evaluating a clause according to the number of different decision levels on which variable of the clause have been assigned. We run the analysis on a portion of our benchmark using Maple as a solver. So this solver had the particularity of storing learned clauses in 3 databases according to the LBD value of the clause, such that relevant clauses, those that are never deleted, are stored in the core database only if they have an LBD value less or equal than 3. The other bases can be updated by removing clauses during the procedure. The figure shows the usage rate of each class according to the LBD value on both propagation, BCP, on the left side, and the conflict analysis on the right side. The x-axis corresponds to the cumulative mean percentage of learned clauses for the training benchmark, and the y-axis is the cumulative mean usage rate. Each point represents the usage rate of learned clauses of a certain LBD that goes from 1 to 10 for a center class, which is colored differently. So for example, if we take this red point, it represents all the clauses of class CPMG that are composed of variables from the 3 sets, property, model, and junction, and have an LBD value less or equal than 8, and the usage rate of this class of clause is a little more than 10% during propagation. So a first observation that we can see from this figure is that a large part of the used clauses are those related to the property, the blue dots. From this study, we present our idea of improving the resolution of SAT-based bounded model checking problems, and it consists in the identification and the protection of learned clauses that seem to be relevant. As you have seen in the previous figure, CP clauses appear to be interesting for the solver, with the usage rate that goes up to 42%, with a low rate of involved clauses that goes a little bit more than 5%. So one of the proposed heuristics is based on this observation. It protects clauses of class CP with an LBD less or equal than 5. The second idea has a mathematical reasoning. It is based on linear programming and aims to predict the usefulness of each learned clauses by determining the adequate LBD value of each class of clauses, with the goal of maximizing the total usage rate of learned clauses with a minimum number of involved clauses. The alternate solution of this approach is to protect clauses of class CP with LBD less or equal than 4, the class CG with LBD less or equal than 9, and remain the same configuration for the remaining classes. We present the result of our experiments using Maple with the two proposed heuristics, HS and HLP. The table displays the number of unsat and sat solved instances, the total number of solved instances, the part2 metric used in all SAT competition, and the cumulated time. The part2 metric computes the penalized average run time, counting at each timeout 2 times the running time cutoff. Our approaches have proven their efficiency on a set of 400 SMV instances, which we compare with the basic Maple strategy. We managed to solve up to 6 more instances and to decrease the overall running time, with a major gain on unsat problem that known to be difficult. We also compared the result with another version that augment the core database to protect learned clauses with LBD less or equal than 4, and seem to deteriorate the performance, resulting in 2 instances less and a part2 metric of 5 hours slower than the original solver. So from these results, we prove that the use of a strategy guided by structural information improves the running time. So to resume, we proposed a generic methodology to classify learned clauses, and we applied it to the special case of BMC. These learned clauses have been classified according to their meaning in the original problem, which helped us to suggest 2 heuristics based on the information carried by the LTL property. The 2 heuristics improve the state-of-the-art approaches, and you can find the source code and the application of the results in our website. In the future, we aim to refine the proposed classification by exploiting the specification of the LTL property and focusing more on tuning the main databases, the tier 2 and local. We also would like to propagate this idea to offer new sharing strategies on parallel SAT solvers. Thank you for your attention. Any question?